Welcome to Lecture 5. In this lecture, we will talk about some of the ideas from linear algebra. I'm not sure if we'll be able to cover all of these in this lecture. Some of them may spill over to the next one, but some of the ideas that we'll be talking about in this lecture and perhaps beyond are linear independence, vector spaces, linear transformations, and orthogonality. Let's start with linear independence. A set of vectors v1, let's maybe write it like this, v1, v2, up to vn, is said to be linearly independent if the only way to satisfy the equation C1v1 plus C2v2 plus plus CNvn equals 0 is to have C1 equals C2 equals equals Cn equals 0. So in other words, if there is any choice of these C's, any choice at all other than this one, this is the only choice we don't want to consider. But if there's any other choice that will make this equation true, then these vectors are not linearly independent. But if this is the only possible choice of the C's that will make this equation true, then the vectors are linearly independent. Now, an equivalent way, and this might give you a little more insight into the idea of linear independence, an equivalent way to say this is that v1, v2, up to vn is linearly independent if and only if no vector in this set can be expressed in terms of the other vectors in the set. So you might say no vector depends entirely on the other vectors, and therefore all the vectors have some degree of independence. That's sort of a hand-waving kind of way of defining things, but I think it might help you to get a little more intuition. It's just that you might say that each vector has some certain piece of information or quality or something that it adds to the set that's a little bit different from what all the others add. Let me be a little more concrete about that. So for instance, let's look at an example. Let's suppose that v1 was equal to the vector 1, 2, 3, and v2 is equal to the vector negative 1, 0, 2. And let's define V3 to be 1, 4, 8. Now, the set V1, V2, V3 is, well, maybe I should ask that question. So I'll say, rather than just telling you the answer, let's ask. So is the set V1, V2, V3 linearly independent? Well, now we're going to learn some ways to test for linear independence in a few minutes, but for right now, all we have to go on is this equation up here: C1V1 plus C2V2 plus dot 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 plus CnVn is equal to 0. So let's look at that. Let's say C1, so we'll say suppose C1V1 plus C2V2 plus C3V3 equals 0. Okay, well, this means then that C1 times 1, 2, 3 plus C2 times negative 1, 0, 2 plus C3 times 1, 4, 8 is equal to 0, 0, 0. Now, this is the same thing as saying C1, 2C1, 3C1 plus a negative C2, 0, 2C2 plus C3, 4C3, 8C3 is equal to 0, 0, 0. And now if we add up the three vectors on the left-hand side, we get C1 minus C2 plus C3, 2C1 plus 4C3, and then 3C1 plus 2C2 plus 8C3, and that vector is equal to 0, 0, 0. So what we see here is that we're getting a system of three equations and three unknowns. We have C1 minus C2 plus C3 is equal to 0, 2C1 plus 4C3 is equal to 0, and 3C1 plus 2C2 plus 8C3 equals 0. These are three linear equations and the three unknowns C1, C2, and C3. Well, we've learned how to use Gaussian elimination to solve a system of equations like that. And so let's try that and see what happens. So we would have, we're going to form the augmented matrix now, and we'll get 1, negative 1, 1, 0, 2, 0, 4, 0, 3, 2, 8, 0. And now we'll start using Gaussian elimination and see what happens. So we're going to add negative 2 times the first row to the second row and negative 3 times the first row to the third row in order to get rid of the 2 and the 3 here in the first column. So we'll have 1, -1, 1, 0. And then when we add -2 times the first row to the second row, -2 times 1 is -2, and 2 would give 0. -2 times -1 is +2, and 0 gives 2. -2 times 1 is -2, and 4 is 2. -2 times 0 is 0, plus 0 is 0. Now we're going to add -3 times the first row to the final row. -3 times 1 is -3, and 3 is 0. -3 times -1 is +3, and 2 makes 5. -3 times 1 is -3, and 8 is 5. And -3 times 0 is 0, plus 0 is 0. Now, what I will do next, we want to eliminate this 5 here. And the easiest way to do this is to multiply the second row by -5/2 and add it to the third row. Now, in previous work, I've tried to avoid fractions, but notice that if we multiply the second row by -5/2, it actually will not introduce any fractions. So let's go ahead and do that. So we have 1, -1, 1, and 0, and 0, 2, 2, 0. And then when we multiply the second row by -5/2 and add it to the third row, okay, -5/2 of 0 is 0, plus 0 gives 0. -5/2 of 2 is -5, and 5 gives 0. -5/2 times 2 is -5, and 5 gives 0. And -5/2 of 0 is 0, plus 0 is 0. Now we have all zeros below the main diagonal, and so we're ready to go back to equation form. And so we have C1 minus C2 plus C3 is equal to 0, and 2C2 plus 2C3 is equal to 0. And that's it. The last equation is just 0 equals 0. So we only have here 2 equations and 3 unknowns. Now notice that the second equation here implies that C2 is equal to -C3. Now let's take that result and plug it in to the first equation. When we do that, when we take the first equation and we take this equation and put them together, we're going to plug in -C3 for C2. Then we get C1 plus 2C3 is equal to 0. And of course, that implies that C1 is equal to -2C3. So what does all this mean? This means we can satisfy the equation C1V1 plus C2V2 plus C3V3 equals 0. We can satisfy that equation by choosing any value we wish for C3 as long as we then choose C2 equals negative C3 and C1 equals negative 2 C3. Now let's just let's just make absolutely sure that that's true. So we're gonna set C1 equal to negative 2 C3 in this equation, and we're going to set C2 equal to negative C3, and let's just make sure that this is going to definitely work. So we would have negative 2 C3 times V1 minus C3, so this is a check, okay? Minus 2C3 times V1 minus C3 times V2 plus C3 V3, and I'll put equals with a question mark to see if that really is equal to 0 for all choices of C3. That's what I'm claiming. So let's see if that's true, okay? Minus 2C3 times V1, and remember V1 is 1, 2, 3. In fact, let me go ahead and copy. Well, I guess I'll just go ahead and write it down. So 1, 2, 3. 1, 2, 3. Minus C3 times V2, and V2 is minus 1, 0, 2. Plus C3 times V3, and V3 is 1, 4, 8. And then we'll say equals question mark 0 for all choices of C3. This is what we're trying to check and see if that statement is true. Okay. So the first vector, when we go ahead and multiply it by negative 2C3, we will get minus 2C3 minus 4C3 minus 6C3. When we multiply the second vector by negative C3, we will get plus, okay, negative C3 times negative 1 is C3, negative C3 times 0 is 0, and negative C3 times 2 is minus 2C3. And then finally, when we multiply the last vector by C3, we get C3, 4C3, 8C3. Equals question mark 0 for all choices of C3. And now if you add up the vectors on the left hand side, we get negative 2C3 plus C3 plus C3. That'll be the first component, and of course negative 2C3 plus C3 plus C3 gives us 0 for the first component. For the second component, we get negative 4C3 plus 0 plus 4C3, so that is 0. And for the last component, minus 6C3 minus 2C3, that makes minus 8C3 plus 8C3, and indeed that gives 0. So we see that indeed, and actually I should... here for this, since I've gone to components on the left hand side, I'll go to components on the right hand side as well. In this equation, the 0 on the right hand side means the 0 vector, but now in going from this first equation to the second equation, I've written components on the left hand side, so I should do the same on the right hand side as well. So that's 0, 0, 0, and likewise down here for this one, 0, 0, 0. And so sure enough, we are getting the expected answer. And notice that we never had to assume anything about C3 at all. So this is true for all choices of C3. And of course, now, if we remind ourselves of what we're doing, then we just said now that this critical equation is going to be true really for an infinite number of combinations of these C1s, C2s, and C3s. The only thing we have to guarantee is that once we pick any C3 we wish, then to make it true, we just need to pick C2 as negative C3 and C1 as negative 2C3. So since there are many different ways to satisfy this equation, that means that these vectors are not linearly independent. They are, in fact, linearly dependent. And again, remember, for it to be linearly independent, we must have that the only way this equation can be satisfied is C1 equals C2 equals C3 equals 0. But that's not the case. There are many other ways to make this equation true. And so, therefore, we say, so V1, V2, V3 is not a linearly independent set of vectors. And furthermore, notice that recall now, after we solve for C2 and C1 in terms of C3, we got this equation right here, which we have just verified. So we have negative 2C3 times V1 minus C3 times V2 plus C3V3 equals 0 for any choice of a C3. We have just found that out. So choose C3 equals 1 to get minus 2V1 minus V2 plus V3 is equal to 0. And notice what this implies. So we could say V1 is equal to V3 minus V2 over 2. We would get that simply by taking this minus 2V1 over to the other side and then dividing by 2. Or we could also say V2 is equal to V3 minus 2V1. Or we could say V3 equals 2V1 plus V2. Now, what is the point here? Well, remember, we said that when vectors are not linearly independent, then at least one of them can be expressed in terms of the others. Well, in this case, all three vectors can be expressed in terms of the others. So, just to remind you, an equivalent way to say this is that the set is linearly independent if and only if no vector in this set can be expressed in terms of the other vectors in the set. So that's equivalent to saying they're linearly independent. So if they're not linearly independent, that means that at least one of them, at least one, must be able to be expressed in terms of the others. But in this case, it turns out that all three of the vectors can be expressed in terms of the other two vectors in the set. So I believe that this using this equation to test for linear independence is a surefire way to go about checking. But this idea of whether or not there is a vector in the set that can be expressed in terms of the others, that definition, I think, might lend a little more insight into the idea of linear independence. But now we want to ask the question, how can we test a set of vectors to see if it is linearly independent? We would like to find a very straightforward, simple test, and so we'll talk about that next. So let's proceed like this. Let's say, suppose we have the set of n vectors v1, v2, up to vn. Suppose also that each of these vectors has m components. Okay? So, how can we easily determine if the set is linearly independent? Okay. There's three cases. One, if n is greater than m, the set of vectors is definitely not linearly independent. So, in other words, if the number of vectors is greater than the number of components in the vectors, then the set cannot be linearly independent. So there's no way, vectors in R3 have three components. So if you have 5 vectors in R3 and you want to know if that set of 5 vectors is linearly independent or not, I can guarantee you it is not linearly independent. If the number of vectors exceeds the number of components, then it is definitely not linearly independent. 2, if n equals m, list the vectors as a matrix and then calculate the determinant. Of the matrix. If the determinant has any value other than 0, the vectors are linearly independent. But if the determinant is 0, the set of vectors is not linearly independent. And then finally, the case that, well, really, I don't know that this case is much more involved than case 2. But anyway, so if n is less than m, what you should do is let's see, how do I want to say this? Let's again list the vectors as a matrix, and then conduct Gaussian elimination. Until you have all zeros below the main diagonal. Then check the diagonal terms. If they are all non-zero, then the set is linearly independent. Otherwise, it is not linearly independent. So let's look at examples. Now the first case is so easy, but we'll go ahead and do an example. So let's just say example 1. And we'll say we'll consider this set of vectors 1, 2, 3, -2, 3, 1, 4, 7, 0, 3, 8, 11. Okay. So here, n, the number of vectors, is equal to 4. The number of components is equal to 3. And so since n is greater than m, this set of vectors is not linearly independent. And then it's just that simple for that case. Now, example 2, we want, for example 2 to be an example of n equals m, and actually the problem that we just did was an example, because here in this example we had the 3 vectors v1, v2, and v3, and they were all had 3 components. So here n is equal to m. So since we already have an example, and we know that these are not linearly independent, we already proved that, let's see how it would work out when we do the test. So I'll take these vectors and transfer them down to the bottom. or copy them, not transfer them, but copy them. So this time, you remember now, our rules say that when n is equal to m, we list the vectors as a matrix and then calculate the determinant. If the determinant has any value other than 0, then the vectors are linearly independent. But if it's 0, then they're not linearly independent. So we're going to list these vectors. 1, 2, 3, -1, 0, 2, 1, 4, 8. And we're going to calculate the determinant of that. So remember our rules for calculating a determinant. We will now, you could, if you wish, go ahead and expand by minors right now, but we can also use some of the procedures of Gaussian elimination to make it a little simpler, and I'll do that. So I'm going to add -2 times the first row to the second row and -3 times the first row to the third row, and let's see what happens. 1, -1, 1, and adding -2 times the first row to the second row will give us 0, 2, 2, and adding -3 times the first row to the last row will give us 0, 5, 5. And now we're ready to easily calculate this determinant. Let's expand down the first column. And so we will get a plus sign from the checkerboard pattern, and then we have that 1 that's up here in the upper left-hand corner, and then we have the determinant of what's left over when we take out the first column and the first row. And that would be 2, 2, 5, 5. And that's all we have, because since we're going down the first column, everything else is multiplied by 0, so we don't have to worry about it. And, of course, then this turns out to be 1 times 10 minus 10, and that is 0. So just that easily we come to the conclusion that this set of vectors is not linearly independent, because the determinant, if it had turned out to be anything else, any other value, then they would be linearly independent. But since it turned out to be 0, they are not linearly independent. And now finally, for example 3, let's suppose that we had this set of vectors. Let's suppose we had 1, 2, 3, and 4, 5, 6. I want to test this set of vectors. Okay, so we're going, since here, oh, and by the way, let me make sure it's clear here. In example 2, as we mentioned, n is equal to 3 and m is equal to 3. And now in this case, n, the number of vectors, is 2, but m is equal to, the number of components is equal to 3. So in this case, what we'll do is list these as a matrix, 4, 5, 6. And then we're going to do Gaussian elimination until we have all zeros below the main diagonal. Here is the main diagonal, and we want to make sure that everything below the main diagonal is 0, and then we'll look at the diagonal terms. So to get rid of the 2 and the 3, of course, we'll just multiply the, to get rid of the 2, we'll add -2 times the first row to the second row. To get rid of the 3, we'll add -3 times the first row to the third row, and let's see what happens. So we get 1, 4, and then -2 times the first row added to the second row will give us 0 and -3. -3 times the first row added to the final row will be 0, -6. Now here is the main diagonal, and we have one remaining term below the main diagonal that is non-zero, and that's this -6, and we can easily get rid of that by multiplying the second row by -2 and adding it to the third row. So when we do that, we get 1, 4, 0, -3, 0, 0. And here is our main diagonal. Now we have reached the point where all the entries below the main diagonal are 0. And so now we look at the main diagonal, and the main diagonal, these numbers 1 and 3 are the main diagonal. Neither one of them is equal to 0, and therefore this set of vectors is linearly independent. However, if either of those numbers along the main diagonal, if either of them or both of them were equal to 0, then these vectors would not be linearly independent. So that's how we test a set of vectors for linear independence. And I believe that really that's enough for this lecture. So we will, let me make some problems, and then we will continue with the other concepts I mentioned at the beginning of the lecture. We'll save those concepts for lecture 6 and maybe even beyond that. Okay, so for the problems for this lecture, the first problem will be from your text 7.4.19. The second one will be problem 7.4.21 from your text, and then the third problem will be given in class. And that concludes lecture 5. So good luck.